All right, good afternoon, everybody. So it is February 24th, and I am doing a video which is a tutorial for using EDAX APEX for EBSD. So a long time ago, I did a video tutorial for doing EBSD using EDAX Team, and EDAX no longer uses Team. So I need to update the tutorial here because this is what is done now with training users. Okay, so I'm doing a new tutorial. So the stage is homed right now. I'm going to switch to quad view. Here's our sample right here. Let me double left click over this. Let me switch to the CCD quad. I'm pushing F5 to switch between single and quad view. Whoops. And then I'm scroll wheel, click, hold, and dragging upward. So your centric working distance on the system is 4 millimeters. The optimal working distance for the EBSD camera is actually 8, although this system is calibrated to work, I believe, between 4 and 16 millimeters. But if you can do EBSD at 8 millimeters, that's what you want to do. Okay, so we're going to stop a little bit short. I want to keep this edge here below the pole piece, and I'm going to show you why in a second here. All right, let me switch back to here. Okay, so now beam voltages for doing EBSD. So 10 kilovolts is about the lowest you can do this effectively, at least on this camera. 30 being the highest. Generally speaking, the coarser the microstructure, the higher the voltage you can use. I think EDAX recommends 20 as a default if you're not really sure one way or the other. The camera responds better as the voltage is increased, so there's that to consider. Generally speaking, though, I find like the response when you switch from 20 to 30 is kind of negligible in terms of the improvement that you get. Like the response improvement tends to be more pronounced when you go from like 10 to 20. Okay. But anyways, so not much gained, I believe, by going higher than 20, but you can gain spatial resolution by going below 20 down to 10. Okay, I know for this sample, this is an Inconel 600 that actually has a chord microstructure, so the middle of the puck here actually has a fairly fine microstructure, so I'm actually going to use 10 for this. Now, as far as the current, as I go up in current, I'm going to get better signal in my patterns, right? Probably use shorter exposure times, get my analysis done quicker, but my beam's going to be bigger, okay? So I'm actually going to put it on 1.6 nanoamps here to kind of show or kind of highlight a few things here, but usually in the nanoamp range is what you want to use here, right? Or otherwise your analysis is going to be a little too slow, okay? It's not uncommon to use like things in the tens of nanoamps here. Again, to some degree, right, your analysis is going to be limited by or your resolution is going to be limited by probe size. So going lower here is going to help you in that regard, okay? But I know with this sample, even though the grains are smaller, right, they're still, fairly micro scale. So you probably don't need to go this low. So I guess we can put this at 6.4. Just to make things a little easier for us, and that should still allow us to resolve everything we need to resolve. All right, so I'm not going to hit wake up because we don't need the fib beam. I'm just going to hit beam on here. All right, so there's the back of the stub. So this is the high side of the stub, and what I'm going to do now is I'm going to drive backwards here till I see the transition from the tilted face to the flat face right here, okay? So you can see that line. That line is not quite parallel from left to right, so I'm going to adjust that. Whoops, hit the wrong button, okay? I had safe stage moves enabled, so no worries here. Let me put this back. What I meant to do was this, align feature. Okay, so we can click and drag along the bottom here and horizontal. Okay, let me do that one more time. Sometimes this kind of overshoots its correction. This is not the best line for this, but it's what we got to work with. Okay, that looks good to me. All right, so we'll move back over to the stub. All right, and here we go. So this dark strip right here, this is where I actually did some in situ PFIB polishing. I thought about including that in the video, but I didn't want to, make the video more convoluted than it needed to be. So I'm going to hold off on that for the time being. At some point, I will add that in. But we want to find something to focus on. Switch to quad view here. Okay, and hit the UFO button. And we're a little long in the working distance, so we'll move to 8 millimeters. Okay, let me pause the image. So I'm going to go over to the EDAX computer now, and I'm going to boot up APEX Suite. So APEX Suite allows you to do everything, okay? EDS, EBSD, simultaneous at the same time. You want to boot up the suite, even if you're, only going to do one or the other. It's better just to do that because then you have all the options available to you. But what we're going to start doing right now is cooling our EDS detector because this is going to take a little while to do. Okay, so you need to open a project. I already have one here, so actually, you know what I'm going to do here? Let me see here. Explorer. Testing. All right, let me delete this one here. I wanted to create a new one. All right. Let me, I'll create a new one. Okay. YouTube tutorials. See if it got rid of that. And then the sample is Ing Connell 600, and it's the second one, so I'm going to call it number 2. Okay, and then it's going to ask us to save it. Since I got rid of the other one, there shouldn't be an issue. Yeah, it's gone. So, okay, perfect. All right. So now up here, we're telling it whether we're doing EDS or EBSD. We need to be in EDS right now. Up here, we have the tabs for the task ribbon, and then here in acquisition, we're going to click the little flap out here, and you want to click this button here, and you want to verify on your pulse processor that your detector is cooling. So right now I can actually see on the back of it that it has a flashing orange LED, which is what you want to see. Okay, once the cooling is done, those will both be green. Okay, sometimes what I find is you have to toggle this and actually push it twice to get it to cool, but it's working right now, so we'll leave it alone. All right, and we will come back now to the SEM side. Okay, we'll go ahead, unpause. Okay, so right now we're at the right working distance, and now because I activated EDAX or APEX, it freezed my CCD, so I need to unpause that so I can see what's going on here. That's really dark. What's going on here? Okay, there we go. Okay, so I need to now tilt, because I'm pre-tilted 45, I need to tilt 25 more degrees. If I do that right now though, I'm going to lose my field of view because I'm not eccentric. So if I go to the navigation module, check ZY link, this is going to impose eccentricity at this working distance. So now I have this little pore here in the middle as my reference point. So I'm going to tilt in 5-degree increments. And you can see what's happening, right? It's keeping the view field approximately as it's tilting. Okay, and then I'm going to recenter it now. I'm going to do one final tweak here when it's done. Okay, so we'll go ahead and leave it right here. So now update the UFO button, and we're basically still at 8 millimeters. So at this point, we could have done this when the sample wasn't tilted to 70. Let's do it now, though. So let's turn on the dynamic focus. We have a pre-tilt of 45, so we're going to click dynamic focus, and we want to make sure automatic is activated. So this is going to keep the entire view field from top to bottom in focus. So the bottom side here is actually higher than the bottom of the image is higher than the top of the image, okay? So I know it doesn't make any sense, right, to say that, but this is actually the high side down here, and this is the low side up here, okay? So by having this activated, it's adjusting for the high tilt of the surface. We can come over to direct adjustments, make sure the crossover is well centered here, right? Again, we can adjust our zoom here. This is, okay, that looks okay. And then we can turn on lens modulator. Okay, we can turn on reduced area if that helps us. And we're trying to minimize the shifting of the image now. Okay, so that's worse. Again, if I pull the vertical crosshair from left to right, that tends to adjust the left to right movement. So that looks pretty good right there. Now if I pull the horizontal crosshair up and down, that adjusts the up and down movement. Okay, looks good. All right, last thing is focus and stig. So get a good focus. Go ahead and adjust your stig here. Okay, that looks good. All right, and then we can, now I have this wide area here, so I'm gonna use a much higher mag here, and if I stay approximately in the middle, my focus should still be okay. I'm gonna increase up to 2500, and I'm going to pause the image right now and switch back to quad view. So at this point now, we're ready to insert our detectors, okay? Let me switch back over to the EDAX side, okay? And let me switch to EBSD. And now here in the task ribbon, we're in the camera tab. This is where we can select insert. So I have the button here on insert. I'm going to switch back over to the microscope side, and you can watch the CCD quad as I insert. Okay, so it's inserting. Okay, so we're going to see it come in from the right here. Okay, very good. Let me switch back over to the EDAX PC, and now we need to do the same thing with the EDS. So I don't have a beam on the, don't worry about this warning, that's okay. I don't have a beam on the sample right now. If I did, it probably would overload the EDS, but since we don't, it's okay. The combination of the beam with the CCD camera will probably do that, but since we don't have a beam on, we won't have to worry about that. But we expand the little flap out here. Now it says the detector is ready. I can verify Actually, my LEDs are not green at the moment. Let me see if that knocks loose here in a minute, but we can go ahead and click move in here. So let me switch it back over to the microscope side, and you can watch. Okay, so I pushed move in, and we can watch as it moves in. So it's going to come in from up here. Okay, so now I know these are safely in, they're not hitting anything. So I can go ahead and pause this now, so I don't have to worry about interference of the CCD signal with the EBSD or the EDS. Okay, so one thing that I'm noticing here is that my EDS detector, it says it's ready, but yet the LEDs on the pulse processor are not green. So what's going on here? Let me cycle this here and let me turn it back on and see if that knocks something loose. So if you can collect EDS data at the same time as doing EBSD, that's usually a good idea. It's better to kind of have it than have it and not need it than vice versa, because you do have that option to do that. So it's certainly doesn't hurt anything. Okay, is it almost cool there? I'm watching the processor on the desktop here. What are you doing? Come on. Equipment is great when it works well, right? What's going on here? Why are you not cooling? Oh, okay, there we go. All right, it went green. All right, so we're good to go now. All right, so I'm going to close this. Okay, let me go back to the microscope side really quick. So what I notice sometimes, and again, I have the CCD paused here. We don't want that overloading the EDS. What I notice here is when you insert the detectors, sometimes you can get a change in your focus here. So you just want to make sure you're focused on your surface here. Sometimes I've seen the stig kind of go out unexpectedly. So we'll just image here and see. I mean, it looks pretty good still. So let me put this back to where it was. Okay, 2500. Are we within the area? Yes, we are. Okay. Okay. All right. So I'm going to switch back to well, actually, I'm going to increase the dwell time here. And let me make sure here. Somehow my dynamic focus got turned off. So let me turn that back on. And let me increase this here. So now the image we're going to collect in Apex is going to look however it is here, at least with the ETD. So again, we can fudge with the contrast here if we want. Again, this isn't going to affect the EBSD results, obviously, but just going to make things a little more aesthetically pleasing here just to watch. Okay, so let's go back to the EDAX side. Now, we're still in the EDS tab, okay? We have to figure out what amp time we're going to use to collect the EDS. So if we come here, if we look down here in the info panel, it's giving us a dead time based on this amp time. We want the amp time, or the dead time, sorry, to be as close to 50% as possible. So this is not bad, but let's see if we can't bump this up a little. So if I make the amp time the next level up, I should be able to increase the dead time a little. So if I come here to this quality panel, click the flap out here, whoops, and then I can, right here where it says speed versus resolution, I'm going to click plus here. And yeah, so that got me just about, so I'm going to go ahead and use this, okay? You have to be in manual mode for this. In manual mode, you can adjust the amp time automatically, or manually, I should say. Okay, so then we have our EDS set, and now we can switch over to EBSD. Okay, so as far as a reference image here, or actually, we're going to, in the acquisition panel here, in the camera tab, click the down arrow. You want to make sure tilt correction is enabled, and the stage tilt is reading what it is, and the pre-tilt is 45 degrees, which it also is, okay? The rest of these parameters, again, this is for the reference image, so it has no bearing on the EBSD data, so this is just used for, you know, collecting a reference, so I keep this fairly low in detail usually. Okay, and then if we click SEM here and then collect, so now this is going to be the same image we're seeing on the microscope side. Now the other option here is we can collect using what's called the FSD. So the FSD is, let me switch back. Okay, the FSD is this guy down here at the bottom of the EBSD, and this is useful for highlighting the grain structure of your sample. So let me switch back to APEX. Okay, so let me go ahead and collect the FSD image. So you can see the difference, right? It just highlights the grain structure much better. Again, has no bearing on the final result. And so now we need to pick some camera settings. So over here, the first thing is the binning. So this refers to the pixel resolution of the pattern. So as I increase the binning, I'm going to improve my signal to noise, but I'm going to lose detail in the patterns, okay? So right now, my pattern intensity fraction is pretty low, okay? So at this exposure. So if I go up to 8x8, you can see what happened is I got a pretty big improvement in this, right? By about a factor of 4, okay? If I go to 16x16, I get another improvement, okay? If I drop to 2x2, this is not really useful for mapping, okay? If you drop to 2x2, you don't really see an improvement over your signal to noise in terms of what you were getting at 4x4. This is really only useful for like point analysis, okay? I wouldn't do this for something like mapping. You're gonna do something in these higher ones. Usually if you have good quality patterns, you can do 8x, or a good quality sample, you can do 8x8, okay? That's gonna give you better signal to noise over 4x4 for the same exposure time. And if you do post-processing with your patterns, like pattern averaging with OIM, it's also going to keep your data size or your data sets more manageable. The problem, though, is this is a little too low for the intensity fraction, okay? So we need to increase our exposure time, but we can't go any higher here, right? We're topped out at 1 millisecond or 1,000 frames a second. So we have to go up to the next slider here, and now we can increase our exposure time here. You can see our frame rate is going down, but our intensity fraction is going up. So now what I find is that an intensity fraction of 0.1 or higher will usually give usable patterns. The more the better in terms of signal to noise, right? So there's a benefit there, but of course, the higher you make this or the lower you make this, the slower your data acquisition is going to be, okay? So let's put this at about 0.2. Which should give us around 500 frames a second. We'll leave it, yeah, we'll leave it at 500 frames a second. okay? The mode, unless you're chasing like the fastest speed possible, you can leave this on standard. If you go to high speed, it cuts the bit depth of the patterns a little bit, and it's really not necessary, again, unless you're doing like thousands of frames a second. Image processing. So this is the image processing that is done to the pattern. If you're doing standard polycrystalline work, enhanced is perfect for this, okay? And then the background. So this is important, okay? So we need to collect a background. So with a polycrystalline sample, it's going to scan over the area and basically collect an averaged pattern, and it's going to call that the background, okay? So if we have a good distribution of grains in our area that we're imaging, we can just do SEM area, okay? If we don't, then we could do SMART, and that will sample a wider area. You have to be careful with SMART, though, because it will, again, goes outside the SEM area, and if you're not careful, if this has like vacuum or something weird in it, it's going to give you a weird background, okay? So let's go ahead and just do SEM area. Okay, and that actually looks about how I would expect, okay? All right, so now back on the microscope side, something I want to point out is the beam blank button, okay? So right now I'm scanning. If I click beam blank right here, that cuts the beam off to the sample, but it doesn't stop the scanning, okay? So this is useful to make sure you're just not, pasting the sample, okay? Because sometimes Apex kind of randomly takes control of the beam when you switch between the tabs, and that can be a little unnerving. So what do we need to do now? Well, we need to tell the system what phases we're looking for. So let's go to the phase tab. So we can see here that we have two phases already selected, FCC and BCC. But since we already know what the material is, we don't need these, and we can tell it, right? Because it's nickel. So if we click search here, click must not be present, change all, and then we're going to find nickel, and we're going to keep clicking until it turns green. And we see here in the search results, we have one option, and then we can get rid of the other two, okay? And the database is fairly extensive. If your material is not in the database, you can load a phase file and generate the phase structure for this, okay? I have done this with random materials that are not in the database, so that can be done as well. But obviously nickel's not that exotic, so this is already perfect. You do want to give the system the least number of phases possible, okay? So if we know that the material is only nickel in terms of its phase, that's all we want to give it, okay? So we're just going to leave it alone at nickel. Now that I actually see this, okay, so this is interesting. So yes, actually here, this is where I didn't realize this, okay? This is where you can select the amp time. So it's actually adjusting the amp time here for us, okay? We don't have the beam on here. I'm going to come back here. I'm going to turn off external control. That gives control back to the SEM. And on pause here. Okay, so I did not know that, okay? If you come here, you can actually do this, okay? And just check auto amp time. I wonder if you can do this also in the EBSD only version of Apex. I'm not sure. I'll have to look into that. But that's interesting. Okay. But this takes care of setting the amp time for us. So there we go. Although there is the option again here to switch to manual if you want to do that. Again, we're targeting a dead time of around 50%. That's what it does if it's automatic. All right, so we have the phase here. Let's go to now the HUF tab. And I'm going to blank the beam here. And we need to make sure that we have the mask here set to the proper value. So as the voltage gets lower, the bands get wider apart and the mask needs to be bigger. So I know from just experimental map collection that 11 by 11, this works perfectly for 10 kilovolts. At 20, you want to use just the 9 by 9. And then I think at 30, you want to use the 7 by 7. Again, I have a table. I don't have it in front of me, but I'm pretty sure that's what you want to use here. I know this definitely for the 10 kilovolts, so we'll leave this at 11 by 11. Let me go ahead and unblank the beam. Well, actually, no, I'm going to come back to the pattern tab, and I'm going to unblank the beam, and this is my beam position. So you can see, right, the pattern changing over on the right. So I want to put this somewhere close to the middle, and once I'm close to the middle, I'm going to let go when I have a decent looking pattern. Okay, and there we go. Let me blank the beam again. And we want to check the solution here. Looks pretty good. Decent confidence index, so anything above 0.1 for a CI is considered high. And then we can tune this. So now what I find with this is you have to hit tune twice, because the first tune result is not that good, but then the next one is fine. Okay, and then if I keep doing it, it works perfectly. Okay, but yes, you want to collect a pattern near the middle, a good one, and then hit tune. This is important for doing your subsequent mapping because it relies on this tuning to give accurate calibrations for what's called the X, Y, and Z star coordinates, okay, without going into all the detail. And at this point now, we are almost ready to collect the map. So let's go to scan now. Okay, and now this gives control back to the microscope. So I'm going to unblank and unpause. Okay, you want to make sure that you are unpaused on your microscope image you're going live. Now, actually, what I found here is I want it to be higher in mag than this. Okay, so I don't know what happened here. I increased the mag to 2500 here. Okay, so what I need to do is collect a new image area. So let me collect image. Okay, I need to do another background here because I changed my analysis area. Okay, we'll come back to pattern. And yep, basically in the middle here. Okay, looks good. Tune, tune. Okay, looks good. Go to scan. And now over here in details, we can tell it what we want to do. Okay, so do we want to save the patterns? Okay, if you're doing post-processing, pattern averaging, you want to do this. Collect simultaneous EDS data. If your scan's going to take a while, you can click auto beam off. So this will turn off the SEM column valves when the system is done doing the map. You can set the step size here between coarse, medium, and fine. Also, you can do it right here, same thing. If you want a custom step size, you can also do that here for manual, or also right here. The default configuration is a hexagonal grid, but you can also do a square grid if you want. And everything else is good to go. Okay, so let's go ahead and click collect. And now if you're doing simultaneous EDS, you want to make sure to give it any elements you may think are relevant here, okay? So I know there's chromium in here and oxygen and nickel, so I'm going to select all of those. What I find is that the system has trouble extracting EDAX information afterwards, so you want to make sure to give it everything at the beginning, because it's kind of difficult to get those details later. Okay, and away we go. So we are seeing right now an IPF or inverse pole figure map superimposed on an image quality or pattern quality map. So they use this term called image quality to refer to the quality of the patterns. So lighter means higher quality. So you can see I have some lovely scratches here, and you can also see where there's grain boundaries as well. That's where we also have lesser pattern quality because two different grains are contributing to the pattern. And we can look at the EDS here. So these are all the different elements. You can turn certain elements off. Okay, so nickel is red, chromium is blue. You can change the colors of these after the fact, but we'll leave this on for now. Okay, now it's doing a histogram stretch with these, so you know, there really probably isn't this much oxygen, especially since we deoxidized the surface. So take that with a grain of salt. So let me turn off oxygen though. Yeah, so usually at the grain boundaries, we see these little chromium-rich precipitate. You can kind of see that here. So anyways, obviously we only told it nickel, so that's the only phase it's going to find, regardless. Okay, confidence index. So this is a measure of how confident the system is in its solution. So green is high confidence and red is poor confidence. So we can see where we have grain boundaries and or scratches, our confidence is not as high, which is understandable. So it looked like actually the spot where I selected the scratches were a little high there, but that's okay. Again, the goal here isn't to, you know, show off my awesome polishing skills, but, you know, just to show you how to use Apex, okay? Now down here, we can actually look at the live pattern as it's scanning. This is the solution for the Kikuchi bands. This is the Huff transform. So basically the Huff transform is a transform applied to the Kikuchi pattern here, and it's a way of actually figuring out what bands are present. So in the Huff transform here, you see there's these different pluses that are at different maxima in the Huff transform. So if we look at, say, the red plus, that corresponds to the red, well, maybe let's use yellow because there's like two kind of close red colors. So the yellow band corresponds to the yellow plus here in the Huff transform. Okay, and based on where these maxima are in the transform, that's telling us the orientation of the band as well as the width of the band, I believe. Okay, so this is how it's figuring out, right, what orientation I have as well as what the crystal structure is. This is the solution, so it's telling us what the bands are, you know, what the zone axes are, and this is the live crystal orientation as it's mapping. This pole figure, unfortunately, it doesn't tell us which pole it's mapping here. I would think this might be 001, but I don't know. It doesn't say that, so it's kind of hard to make heads or tails of that. If we come back here to just the live pattern, and then we go to legend here. So for the IPF, so in a cubic crystal, all of our orientations are contained inside this one triangular snippet of the stereographic projection. Okay, so if we use red here means perfectly 001, blue is perfectly 111, and green is perfectly 101. Okay, so this refers to the set of planes that is parallel to the surface. Okay, so right, this is deep in the green, so this is probably close to 101, and then we have, you know, some nice red here, which is 001, and some nice dark blue here, which is 111. And so any color combination of these can represent any of the in between colors, okay, which is pretty neat. So we can represent all that orientation. Now, of course, the variations of 001 would also be red. So 100 would also be red. 111 or 110 would also be green, and 1 bar 1 would also be blue. Okay, and we can see here that we have this deep green here for the CI for each line, which is good. It's telling us that we have high confidence index for each line. So we got some good results here. Okay, now it's saving the map data. Now I'm back on the microscope side. I'm gonna go ahead and blank the beam here, so we're not pasting the sample. And now it's giving us a synopsis. Okay, so number of points that were indexed, number of points with high CI, the average CI for the whole map, which is really good. And we can go ahead and click done. And now over here in the project tree, so we're seeing, right, the project name, the sample name, and then every time we do image area and then collect a map, we're going to get an area and then the map under the area, okay? So just doing collect image doesn't make the area. We have to then collect a map first, and then it will populate an area. So if we collect another map for this area, it will produce another map, okay? So now to export this for analysis to OIM, all we have to do is double left click on this, and that exports it to OIM, okay? And at some point, I will do another video describing the post-processing of the data because I know it's very useful. You know, quite frankly, that's something I'm still learning myself. So that's why I haven't made the video on that, because that's something I have not entirely wrapped my head around myself. So, you know, I want to make sure I give you, you know, the most accurate information I can. There are people who are experts in using OIM who have told me that they only understand about like 35 to 40% of what OIM can do, which is, you know, just tells you how powerful this software is. You know, if I had to put a number on how much of it I can use and understand, I'd probably say like 10%, maybe, if, you know, on a good day. So it's very powerful stuff. There's a lot you can do with it. So, and at some point I'll do a tutorial on some of the basic processing you can do. But we'll leave this alone for now. Go ahead and close this. Okay, so when we are finished here doing our EBSD, okay, let's come back to the camera tab here. And now we can take out the camera. So actually, okay, one more thing here. Let me go back to the microscope side here and show this to you. Let me release the beam here. Let me go back to the microscope side. So sometimes people they want to do analysis on other areas on the sample, okay? So this is a little tricky to do. You have this EBSD camera in here. If you're doing like a big stage move, again, we have enable safe stage moves activated. The system should account for that, and there shouldn't be an issue, okay? What you don't want to do at this point with these inserted is something like homing the stage, okay? That's a no-no because you're probably going to hit the detectors here, okay? But if I mag out here, right, so let's say I wanted to just come back over here, okay? So that's a small move. Okay, I can go ahead and focus on this, hit the UFO button. Okay, I'm a little bit short in the, or too close in the working distance. So I'm going to go ahead and go to 8. So again, these are small stage moves. Now I'm not moving between samples, okay? I'm still, right, I'm still basically on this guy here, okay? If you wanted to switch between samples, for that, you want to take the camera out and the EDS out and then move over to the other sample and then put them back in, okay? But we're not going to worry about that for now. But the point here is you have to be careful with the stage movements when your detectors are inserted. Mainly the EBSD. It's not so much an issue with the EDS, but more so with the EBSD. Okay, so if we're done here, let me go ahead and pause this, and let's go back to the EDAX side. Okay, so right here, this is the retract button. So I'm going to go back to the SEM side now. I'm going to unpause so we see this live. I need a stick to push the button here. There we go. All right. And then I'm going to push retract here. So you can't see me doing this, but I want you to see the camera actually going out. Okay, so there's the camera going out. All right, I'm going to switch back to the EDAX side here. Okay, so now we might be able to retract the detector for the EDS without going back to the EDS tab. I think if we click on acquisition, yes, we can do this here. Okay, so I learned something important today, okay? So we probably don't need to boot up the suite to do simultaneous EDS with EBSD, because what we saw here was inside phase, we can change the amp time right here in the EDS panel, okay? And then right here in the acquisition panel, which is active whether we're in phase or in camera, we have the cooling as well as the slide control, okay? So let me go back to the microscope side, and then because I activated Apex, it took control back, so it automatically paused my CCD to prevent interference. So now I'm clicking the move out button so you can watch the EDS move out. Now I'm going to go back to the Apex side here. Okay, and now it's out. And we can leave the cooling on. It'll turn off automatically when it's not when it's idle for so much time. So there's no need to turn this off now. You don't have to worry about this if you vent the chamber because this is there's a self-contained vacuum inside of the detector, so there's no need to worry about contaminating it. Okay, you can just leave the cooling on. Let me click close, and we'll go ahead and close this. So now actually, let's boot up the EBSD only here, and let's see if my hypothesis is correct here. Excuse me, I'm going to get a drink here while this is loading. Okay, so here's our slide control, right? So you notice, right, only no two tabs up here, okay? And then scan. Aha. Okay, so the option to control, whoops. There it is. Okay, so perfect. All right, so no, we don't have to boot up the suite. Okay, we can control everything we need as far as the EDS right here. All right, so I had no idea, right, that was actually in the phase tab. I don't know why they put that in the phase tab. I guess it kind of makes sense. Some of the placements of these control panels are a little odd to me, but anyways, that's where they put it. So, all right, so we learned that we don't have to boot up suite. We can just boot up Apex EBSD. So, but again, it doesn't hurt to boot up the suite anyway. Okay, so let me go back. So now I swear we're done with the EDAX side. All right, so finishing up here. Make sure that we have unpaused the CCD quad. If we're done here, we want to make sure we've disabled dynamic focus. We want to tilt back to 0, but before we do that, let's we don't want to change anything as far as the ZY link. Let's leave that on for now. Let's go live with the SEM image, and we'll tilt back to 0. Okay, and then now we can disable the ZY link. You do want to make sure to turn this off to avoid confusing the next user, okay? If the next user tries to use the system with this enabled and tries to set eccentric height the normal way, that person is going to be very confused, okay? Same thing if you have dynamic focus enabled, okay, and the person isn't aware of it, okay? So be a good user, make sure those are deactivated when you are done with your EBSD. At this point, we can pause and turn the beam off. Now, the other thing too here that I wanted to point out, there is an option down here for tilt correction, okay? You don't need to enable this at any point when you're doing EBSD because that is enabled automatically in Apex, okay? If you enable this and also enable it in Apex, you're going to extra distort your image and you don't want to do that, okay? So you don't need to worry about activating this at all. Again, this is taken care of in Apex as I pointed out. And from here we can go ahead and home the stage. All right, almost done. All right, so that concludes the demo for using EDAX APEX for EBSD data collection. All right, take care, everyone.